Hey, welcome back. All right, so we just finished up with box blur. Let's just sort of review what we did. So we kind of looked at this in three different ways, although two of them were kind of similar. Basically, we had our original where we're building the frame and then we're populating the frame. Then after that, we did basically, well, oh, look at that. You see, this is why I come back here. All right, so we kind of did both in one shot here with the next one, so that's probably a bit better. And then at the end here, we looked at it in a different way where we're sort of just flipping it around and we're looking at the values in the original and just seeing, well, which of these is it gonna contribute to in terms of the sum. Now, something I didn't talk about is which is the better algorithm. And part of the reason is because I don't really know, to be honest. Could be any of these. Well, okay, I would say that probably it's not the bottom one, because we were able to do that more efficiently up here. But I don't think it's this one. I mean, it's hard to say. Like I was saying, we don't have to keep checking the image again and again, but I don't know if array lookups are really that costly anyway, so I don't know if that's something we need to really worry about. The main thing is it reveals two ways that we sort of can look at it if we want to. So another disadvantage is, you remember, we had to do this map at the end, whereas we were able to do everything all at once with this one. Okay, now the reason I wanted to show you this stuff again is because we're going to use some of the same strategies for this next one. So this is Minesweeper. Now you might be familiar with Minesweeper. I mean, if you've used a Windows PC, it's a built-in game and it's very exciting. So let's see specifically what this challenge is asking us about.
In the popular Minesweeper game, you have a board with some mines, and those cells that don't contain a mine have a number in it that indicates the total number of mines in the neighboring cells. Starting off with some arrangement of mines, we want to create a Minesweeper game setup.
Okay. So we've got an example here. Let's say we start out with a matrix and it's true, false, 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 true, false, false, false. And well, what do the trues and falses represent? It represents if you have a mine or not. So basically the idea is that the trues are mines, the falses are not mines. And what we want the output to look like is this. Now, if you've played Minesweeper before, you might be a little surprised by this because you might be thinking, well, these aren't they mines? Like, shouldn't we have like the little spike balls here and here? And not in this challenge. So in this challenge, basically the idea is that the mines are just going to work like regular tiles. They're just going to say, well, how many mines are there around me? And they're not going to count themselves. So that right off the bat is going to be one major difference between this and the previous challenge, that we're not counting the square itself, whereas in the previous one, we were. Okay, so let's go through this one. We're going to do something really similar. We're going to start by, let's see. Let me check my constraints for just a sec. It's a rectangular matrix, so it's not guaranteed to be square. Might as well do what we did last time. So we said call height is assigned the value of matrix.length, and row length is assigned the value of matrix at 0.length. And something we didn't do last time, which is now occurring to me, is that we should make these constant values because they're not going to change. It's not like we're going to have to reassign these at some point. Our matrix is not going to change sizes. So good, constant. I feel better about that. All right, and then let's say what should we call our new matrix? Like minefield, I guess? Yeah, minefield. Although, I don't know, maybe that's a more appropriate name for like the original matrix, because that's the one actually giving us the mines, but let's call it minefield, just, for fun. Okay, so minefield starts as this empty array. and we're going to build it up. So again, like we've seen in the past, we could use like a dot fill here and stuff like that, but we're not going to do that this time. Instead, we're just going to use loops like we did with the previous one. I guess I'll use X and Y. Oh, and another thing I forgot to mention last time is that it might seem a little strange that I'm using X and Y as opposed to like I and J or something like that. It's different than like a Cartesian plane, you know, like ordered pairs, that kind of stuff. The coordinates aren't really working exactly the same here. And so that's, yeah, that can be a little frustrating, you know, like if you had like an X value of 2, 1, it wouldn't normally be like go down 2 and then right to the 1. It would be flipped in a couple of ways. So that can be a bit confusing, but the reason I like to do it that way is so that I can just say something like minefield at X at Y. So that's, I guess, kind of natural. And also it sort of pairs with the DX and DY that we saw in the last one that we're probably going to see in this one as well. So let's return minefield at the end. What are we going to do with minefield? Well, we'll say the same thing we did before. So we'll say let row be this empty array, and at the end of the outer loop, we're going to do a minefield dot push row. This is pretty common for like if you want to fill up a new matrix, that we're going to have 2 nested loops. The outer loop is going to start a row and it's going to fill up that row in here. So here we'll do like, you know, a row dot push of something, maybe a 0 to begin with. And then we're going to do a minefield dot push of that row. So minefield gets the entire row, which is itself an array that we're filling up within the inner loop. Okay, so that's the right size. That's good. That's the right size. That's the right size. Okay, let's make it not just the right size, but the right values too. We might as well do that, right? So let's say let neighboring mines be assigned the value of 0. And I know that's kind of a long name, but you know, I want it to speak for itself, right? I want it to be clear. And then we're going to be pushing neighboring mines in there. And also, if you're wondering about the spelling here, I'm Canadian, sorry. All right, so neighboring mines is 0. And then we're going to do the same thing we did before. So we'll do our for loop. Basically, the idea is now, let's say we're looking at this one, right? We want to be considering its neighbors. So specifically, we want to be looking at this one here. You can barely see that color here. Let's go with 2 brand new colors. Let's go with yellow. Oh yeah. And let's go with orange. Okay, so we want to be considering that one, and that one. Now, if they existed, we also would consider all these ones around here, but we need to sort of ask ourselves, do those exist? The main thing is, just like in the previous one, we're going to be doing x minus 1, y minus 1, x minus 1, y, x minus 1, y plus 1. And then we'll do x, y minus 1, x, y. Well, actually not x, y in this case. We'll skip that one, and we'll talk about how we're going to do that in just a sec. But then we're going to say x, y plus 1, and then x plus 1, y minus 1, x plus 1, y, x plus 1, y plus 1. Okay, great. So we'll do the same strategy as we did before. We'll say let dx be assigned a value of -1. dx is going to increment itself until it gets to +1. And we'll do the same thing with y. We'll say let dy be -1. dy is less than or equal to 1. dy plus plus. So then the problem here is we need to check, number 1, is it the element itself? So basically, we need for these to not both be 0. If they're both 0, then, well, we're talking about the number itself. We shouldn't count the mine itself. So instead, we'll say something like this. We'll say if dx is not equal to 0, or dy is not equal to 0. And that's like a very literal way of doing it. So we're saying if one of these is non-zero, then we're fine. You know, we can have one of them being 0, but the other being -1 or something like that, and that's not going to be a problem. But if they're both 0, that's when it is a problem. We can also say something like this. You know, that's a shorter way of saying the same thing, because if these wait a sec, is that what I want? Do I want an and or an or? I guess I want or actually, because basically it's saying, well, the only circumstance under which this is going to be typecast to false is if dx and dy are both 0. And I guess that's what we don't want, right? So we'd have to put like a not and wrap it up and stuff like that. So let's just go with what we had before. If dx is not 0 or dy is not 0. So this is going to work unless they're the same. Okay, so great. So basically that's if it's not the mine itself. That's if it's one of the neighbors. But then we also need to check this. So we'll say let temp x be assigned the value of x plus dx. We're going to let temp y be assigned the value of y plus dy. And then we're going to check if it's in range. We'll say if temp x in matrix and temp y in matrix at 0. Now keep in mind, just like we saw in the previous ones, this is not checking. This is not the same as saying like something like this, like, you know, matrix dot includes temp x. That's what it looks like, but that's not what it is. So this is checking if temp x is an element within matrix. This one up here is checking if it's an index within matrix. So temp x might, like in this case, well, actually in this case, temp y, both of them, yeah, there are going to be situations where temp x is going to go like off the grid here. It's going to be too large, or temp y would be too small, like temp y would be -1. So matrix at 0 doesn't have an index that's -1. So basically that'll fail. The in will fail if it's not one of the indices that we're looking for. There are other ways of doing that, but I like this in keyword. I don't know. Hopefully I don't find out later that it has no support and you're not supposed to use it. But anyway, I'm going to use it for now. It's kind of nice. I think it really sets you free in a problem just like this one specifically. Okay, so if temp x is in matrix and temp y is in matrix at 0, and if matrix at temp x, temp y. And we know we can do this at this point because we know at this point that these indices have been confirmed to be within the range of the matrix. They're proper coordinates. They're legitimate coordinates. Okay, so basically what we're saying, if matrix, if there is a true there, so really just if matrix at temp x at temp y. This is either going to be true or false, right? So it's already a Boolean. We don't need to say like if it equals true, you know, like that's totally redundant. If it's true, then it's already true. Okay, so if this, then what we want to say is neighboring mines plus plus. There's another mine in the vicinity. That's all we're really saying. We don't need to like push this into some value or anything like that. We're just increasing the value of it. Great. So have we... Yeah, okay. Let's run the tests. Oh, look at that. Okay, so that's nice. It's passing all the visible tests here. It's giving us the minefield we're looking for, so that's great. Might as well submit it, see if it passes all the hidden tests as well. And there we go. Okay, so that's pretty not bad. Congratulations on that one, and we'll just close that for now. Ooh, look at this. Okay, so this is pretty heavy because we have cleared the island of knowledge. That feels pretty good. All right, and we made it to a new level. Okay, so we're what, recruit? Yeah, recruit 5. Wow, we're really we're getting there. All right, so let's see. This is pretty good, I think. I mean, just we could have done something like the previous one where basically we build out the new matrix and then separately go through it and fill it with values. We could have done that. We chose not to do that this time because it might be a bit repetitive. But the main thing is we could have done it that way. We don't have to. It's all getting done sort of at once here. So that's kind of nice. That's I think it's a good way of doing it. I'm pretty happy with the algorithm. Can it be done differently? Well, yeah. I mean, there are a few things we could do differently here. Like for example, this part here. Just to clean it up a little bit. Like these are and statements, right? So the only circumstance under which it would make it past these ands is if these were both already true. If any of these are false, it's not even going to bother checking the next one. So I could just take this part and put it up in here, and that should work. I mean, directly nested ifs like that are probably something we don't generally want to see. So does it still run like this? Yeah, it does. And let's just make it a little more easy to look at by doing that. Okay, I mean, technically we could probably even get this all together as like one if, but this is probably fine. Yeah, it's probably fine. Okay, great. So let's not do that. Let's think about another way we could do this problem. Is there another way we could do this problem? Well, we found that with the previous one, we were able to sort of flip it around like this. And sorry, that looks kind of atrocious right now. Let's clear all this stuff. So we were able to flip it around, and now we want to do the same sort of thing with this one. So, well, actually, maybe this is we already have a visual here, right? So, what we were doing before, what we were doing in this algorithm currently, is we're looking at every cell in our new matrix, and we're just saying, okay, we're looking at which one? This cell right now? Okay, great. So what's around that? And then we're just saying like, is this a mine? Is that a mine? Is that a mine? Is this even possible? Is that possible? Is that, you know, like there's a lot of stuff we're doing. And then we move on to other ones. We say like, for example, this guy over here. And now, again, we're kind of repeating ourselves because we're saying, is that a mine? 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 Okay, so the point is, we don't need to keep checking where the mines are. We kind of already know where the mines are. So the mines are here and here. So we're going to flip this around. We're going to take all this stuff and we're going to paste it in up here. And we're going to reattempt. So we're going to try this over again. Let's get that on the next slide just for a bit of breathing room. Okay, and then what are we going to change here? It's this Derf. Let's change that, and yeah, okay, so let's make it a 0 now. Yeah, just a 0. So minefield should basically just be all zeros at this point, and great, yeah, that's what we're looking for. That's actually the answer to this one. Great. Okay, so coincidence, but we'll take it, I guess. Okay, so it's all zeros here. Now what I want to do is at this point go through original matrix, and for every mine, add 1 to all its neighbors. Okay, so similar, you know, it's going to be very similar to the other method, except it's just flipping it around. So again, I don't know which one is going to be like better, but this is another way of doing it. Okay, so we'll say for let x be assigned the value 0. Oh, yeah, and by the way, I meant to mention this before, but if anyone's wondering, like, is it actually okay that you're using x here? Like, you use an x above. I can see it. It's on screen right now. So is that okay? Like, are you allowed to do that? And the answer is yes. In fact, it's a double yes, because that would be okay regardless, but it's especially okay because of the block scoping of this let keyword, right? So because we're using let and not like a var or something like that, that means that x is bound to just the contents of this for loop. If we tried to get x outside, like from outside here, if I did like a return x, in fact, maybe if you're not convinced here, return x, and then it's going to say, what are you talking about? X isn't defined. There's no x. And it's kind of outsmarting the editor here because it's showing it in blue as though it should be something that it recognizes. So it's not used to block scoping. So, okay, just all that to say, you know, it's okay that we're reusing this. Okay, so if it's a mine, which means if matrix at x at y, and that's it, right? Because it's going to be a true if it's a mine. So if it's a mine, then we're going to add 1 to all neighbors. And how are we going to do that? Well, what are all of the neighbors? How can we get all the neighbors? We're going to do this again. No, not like that. We're going to do for let dx be assigned the value of -1, dx is less than or equal to 1, dx plus plus, and within that we're going to do a dy, which also starts at -1, also grows until it reaches +1, and also increments at every step of the way. And then from there, we'll just say, I guess the same thing as what we did before, let temp x be assigned the value of x plus dx, let temp y be assigned the value of y plus dy. And then from there, we have these things. We can just say, well, are they in range if temp x is in matrix and temp y is in matrix at 0. And keep in mind, this, like we saw in the previous challenge, this is exactly equivalent to saying if temp x is greater than or equal to 0 and less than or equal to the length of this matrix minus 1. Same thing. It's just easier to write it this way. Okay, so if these neighbors, oh, and all of this should be wrapped in, I should have just let this happen. But anyway, it should be wrapped in one of these. If dx is not equal to 0 or dy is not equal to 0. Okay, maybe afterwards we'll take a look at why I'm building that part in and what would happen if it wasn't there. So, oh, so many nested blocks here. Look at how deep it's getting. Okay, so it's making me a bit uncomfortable, but we'll see. Okay, so we want to say matrix at temp x at temp y plus plus. You know, we're just adding 1 to it. So, but it's not matrix that we want to be adding 1 to. It's minefield, actually. So minefield at temp x, temp y. And so maybe we should actually be checking if these are in minefield. Wait, what happened there? Okay. So, yeah, there we go. Minefield. Yeah, okay. So let's try that. Let's see if that runs. Great. It works. Is it better? In some ways, I'd say yeah, it is. Like the reason I say that is because I'm just looking at this particular example, and I notice this one only has 2 trues, right? Like there are only 2 mines in here. So when we're looking at the previous one, this is guaranteed to check all of its neighbors regardless. So it'll say, okay, we've got a thing here. What do we have around us? Are there mines? Yeah, there's a mine. Okay, great. What do we have here? Any mines around? Yeah, a couple mines. Okay, great. What do we have around us? Any mines? Yeah, a mine? Okay, great. So we're checking for each one. We're looking all around regardless. Whereas with this other algorithm, the only circumstance under which we look at the neighbors is if we have a true here. So the only way this one would take as long to execute, I guess, is if they were like all mines. I mean, yeah. So I think probably the second one is a bit better, but again, it is kind of doing the same thing, but in opposite order, right? Like this one has 4 levels of for loops, I think. We've got the x one, the y one, the dx one, the dy one. So for loop within a for loop within a for loop within a for loop. And we have the same thing up here, right? For loop, for loop, for loop, for loop, for loop. But the thing is, you know, you might be looking at that and thinking, okay, so I guess that means it's big O of n to the power 4. But no, in this case it's not, because like these for loops in here, keep in mind, they're only covering 3 elements every time. That's a constant. It doesn't depend on the size of our field here. This is only going to cover 3 elements every time. Whereas if we look at these ones over here, these do depend on the size of the field. I mean, if this was wider, if it was longer, then it would change both of these values, and so it would scale up. So this would be more like a big O of n times m, where n is, you know, the length and m is the width or something like that, right? Because they could be different. It's a rectangular board after all. All right, so we'll make a comment. Probably better. Big O of n plus m or something. Might as well spell that correctly. And then this one down here is, I think, also big O of n plus m or something. Now, something I've been meaning to mention is when we talk about big O, like, you know, if we say this one's big O of n, like not all big O of n algorithms are going to be the same. Not all of them are going to be equally optimized. They're just within the same like family of complexity, you know, like they're related, you know, they're going to scale up similarly, but that doesn't mean we can't optimize it further without changing the time complexity. So keep that in mind, you know, there are little like micro optimizations we can make, and it comes right down to like, you know, how are you multiplying things? Are you using exponentiation? These kinds of things. So, you know, we can really get into the finer details, but start with time complexity. Start with big O. You know, start by having something that's like big O of n, big O of log n, and then from there we can talk about optimizing it. There's no sense in optimizing, like getting super optimal in the fine details of an algorithm that's like big O of n to the power of 4 or something like that, or like n factorial. Make the algorithm good first, you know, make the time complexity good, and then we can get into the micro optimizations, which we really tend to see like in production sort of thing. So you don't have to worry about all that right now. Okay, so that's I think that's it, right? Did this pass all the hidden tests? I don't remember if I tried, but yeah, okay, it's passing all the hidden tests. Great. So if you want to take a look at this one, this is solution number 5367, JS the game, and it's going to be right here waiting for you in case you want to take a look at it. As for now,